students, welcome to my class. I am Megha Chaturvedi and this is the class of electromagnetic theory. And in this class, I will provide the notes and lectures of the topic Maxwell equation and the wave equation in lossy medium. So first of all, we see that the Maxwell equation having the first law, Gauss law, which states that the electric flux through any closed surface is equals to the electric charge enclosed by the surface. Gauss law, which describes the relation between electric charge and electric field it produces. This is often pictured in terms of electric field lines originated from positive charges and terminating on negative charges and indicated the direction of electric field at each point in space. Now, Gauss law for magnetism, it states that the magnetic field flux through any closed surface will be zero. This is equivalent to the statement that magnetic field lines are continuous, having no beginning or end. Any magnetic field lines entering the region enclosed by surface must also leave it. No magnetic monopoles where magnetic field lines would terminate are known as to exist. Now the third one is Faraday's law. A changing magnetic field induces an electromotive force and hence an electric field. The direction of EMF opposes the change. Equation is Faraday's law of induction and includes Lenz's law. The electric field from a changing magnetic field has field lines that form closed loop without any beginning or end. Now the fourth one is Ampere circuital law. Magnetic field are generated by moving charges or by changing electric field. This is the fourth equation of Maxwell equation, which encompasses Ampere's law and add another source of magnetic field, namely changing electric field. This is the diagrammatically we understand that how changing E and H field propagate through space. This is the all four equation of Maxwell in the integration form. That is Gauss law is the first equation, second one is Gauss law for magnetism, third one is Faraday's law, and fourth one is Ampere's Maxwell law. Now we can move to the next topic, in which integral form of Maxwell equation we see. Let's have a look in the Gauss law for electrostatic, which states that the total electric flux through a closed surface is proportional to the enclosed electric charge. Mathematically, we can express as del dot E is equals to rho upon epsilon naught, where E is electric field, ds is the infinite area element, and closed integral of E over ds gives the electric flux. Now the Gauss laws for magnetism, this states that the total magnetic flux through a closed surface is zero. This basically means that the magnetic monopoles cannot exist. We know that when a uh, magnet is broken down into smaller pieces, each piece will have its own north and south pole. One cannot isolate a single pole. Magnetic poles always exist in pair. Must be, this is the must condition, that magnetic poles exist in pair and there is no net magnetic field outflow through a closed surface. Mathematically, we can written as del dot B is equals to 0, where B is the magnetic field, D is the infinite area element, and B is the magnetic field in the closed integral form. Now the Faraday law of induction, which states that changing magnetic flux always generated an EMF that is equals to negative to the of the rate of change of magnetic flux enclosed by the surface. The EMF is basically voltage that can be obtained from integrating the electric field. Mathematically, Maxwell Faraday law becomes del cross E is equals to negative del B by del T. This is the electromagnetic induction is the which is the source of all power, operating principle of electric generator. Now the Ampere circuital law, which states or relates the magnetic field around a closed loop to the electric current passing through the loop. Although named after Ampere, it was actually derived by Maxwell using hydrodynamics, which is the study of liquid flow. And mathematically, we can express this as del cross B is equals to mu naught into J plus mu naught epsilon naught dot del E by del T, where B is the magnetic field, dl is the infinite line element, and the line integral of B gives the current flowing through the wire. Now Maxwell added a term to this equation known as displacement current, which will be defined as by the rate of change in electric field. Its origin is not due to actual charge flow but due to the changing electric field. Mathematically, it is id is equals to epsilon naught a dot del E by del T, where id is the displacement current, E is the electric field, and A is the surface area. A prominent example where this comes to play is the case of capacitor. There is no charge difference between the plates of capacitor when it first begins to charge. The modified Maxwell circuital law now becomes integration summation of integration B dot dl is equals to mu naught bracket uh, equal summation I plus displacement current. Now the Maxwell's first equation derived from the Gauss law of electrostatics as per the Gauss law of electrostatics, which will be defined as the electric field multiplied by the area of surface projected in a plane and perpendicular to the field, applying in this as a divergence theorem, which is the second equation. From equation 1 and 2 we get triple integration del dot E dV is equals to q upon epsilon naught dV. We need to define charge as the integral of volume charge density, q is equals to triple integral rho dV, where del dot E is rho upon epsilon naught, Maxwell first equation. Now the Maxwell's second equation, which is derived from the Gauss law of magnetism. According to the Gauss law of magnetism, magnetic field flux through any closed surface is zero, which is equivalent to the statement that magnetic field lines are continuous. They have no beginning or end. Thus, any magnetic field line entering the region enclosed by the surface must leave it too. From equation 1 and 2 we get del dot B dV is equals to 0, which is the triple integration. And here, to satisfy the above equation, we can either have triple integration del V is equals to 0 or del dot B is equals to 0, which is the Maxwell's second equation. Now the Maxwell's third equation, which is derived from the Faraday's law of induction, in which summation of integral E dot dl is equals to minus double integration dv by dt dot ds, which is the first equation, and we get second equation from applying the Stokes theorem. So we get from first and second equation as double integration del cross E ds is equals to double integration minus b upon dt dot ds, which is the Maxwell third equation. Now the Maxwell fourth equation, which is derived from the Ampere circuital law. From equation 1 and 2 we can see that integration del cross B dot ds is equals to mu naught J plus JD, where J is the current density and JD is the displacement current density. Now our next topic we will move on to uniform plane waves in lossy dielectric. Practically all dielectric material exhibit some conductivity. So during analysis of the uniform plane waves through dielectric, with which amount of conductivity we cannot neglect zero by assuming it to be zero. Due to certain conductivity, certain amount of loss in the medium take place. Let us consider uniform plane wave travel in z direction through lossy dielectric. The wave equation of the for the electric field vector E is given by Ex is equals to Em e to the power minus alpha z dot Ej omega t minus beta z plus Em into E to the power alpha z dot e to the power j omega t plus beta z. And the propagation constant for lossy dielectric will be equals to under root sigma plus j omega epsilon into j omega mu. Rearranging the terms, we will get in this form. And we know that propagation constant is equals to alpha plus j beta. So final equation will be in this form. Now our next topic is Poynting vector and Poynting theorem. When electromagnetic wave travel in space, it carries energy and energy density, which will be always associated with electric field and magnetic field. The rate of energy travel through per unit area, that is amount of energy flowing through per unit area in the perpendicular direction to the incident energy per unit time, is called Poynting vector. And mathematically, Poynting vector is represented as P is equals to E cross E or E cross B upon mu, which shows the direction of Poynting vector is perpendicular to the plane containing E and H. Poynting vector is also called as instantaneous energy flux density, and here the rate of energy transfer P is perpendicular to both E and H. Since it represents the rate of energy transfer per unit area and its unit is watt per meter square. It also states that the net power flowing out of a given volume is equals to time rate of decrease of stored electromagnetic energy in that volume decreased by the conduction losses. That is, total power leaving the volume is equals to rate of decrease of stored electromagnetic energy minus ohmic power dissipated due to motion of charge. Our key concept is skin depth, which will be defined as the depth of it into a conductor at which the current density has fallen to about 37% of its value of the surface. Now the reflection coefficient, it is the ratio of amplitude of the reflected wave to the amplitude of the incident wave. Transmission coefficient is the ratio of amplitude of the transmitted wave to the amplitude of the incident wave. And the Brewster angle is the angle of incident at which a wave with a specific polarization is completely transmitted through a dielectric surface with no reflection. These are the condition and formula, which is tan theta b is equals to n2 upon n1, where n1 and n2 are refractive indices of the two media. Thank you.